Here we can see 5 sums to be done in the binary number system. Let's have a look at the first one, which is this one here, which is saying add up 0 to the base 2 plus 0 to the base 2. Well, obviously the result in this particular case is 0, and I'll put a little 2 there to emphasize that we're in base 2. If we have a look at the addition of the next one here, we can see we have a 0 to the base 2 added to 1 to the base 2, which is obviously going to give us the result of 1. And again, I'll put a little 2 there. The next one, if we have a look, that is 1 plus 0, again in base of 2, i.e. binary, and the result of that is actually going to be 1 as well. If we come to the next addition, which is this one here, we can see that that is 1 to the base 2 plus 1 to the base 2. Now 1 plus 1 is obviously 2, and 2 in binary looks like this. It's a 1 followed by a 0, and I'll put a little 2 there to emphasize the fact that we're dealing with binary. Now that might look like 10, but remember it's in binary. If you're unclear of binary, go back and look at some of the previous videos. Now the last one is this one here, and we can see that we have 3 ones to be added together, and of course 3 ones give us 3, and 3 in binary is 1, 1, and I'll put a little 2 there to remind us that we're in the base of 2, i.e. binary. So there you can see the addition of numbers in the binary number system. Here we can see 2 8-bit numbers to be added up, and we can see again that they're in binary. Now we add up by taking each column in turn. Let's have a look at this column here. Now a 0 plus a 0 is obviously a 0. Go to the next column. That gives us a 0 plus a 1, which is a 1. The next column here is a 1 plus a 0, which gives us a 1. Now the next column here is 1 plus 1, which is 2. Now this is where we have to be a little careful. Now 2, well, we have to do that as follows. It's a 0 down and the carry 1, because we cannot put 1 0 in one column. We have to carry it over to the next column. Now this particular column now is a 0 plus a 0 plus the 1 that was carried, which gives us obviously a 1. Now we come here to add up this column, which is a 1 plus a 1, which is 2, which is 0 down carry 1. Again, we have to carry there. And now we come to add this column, and what we can see is we have a 1 plus a 1 plus the carry, i.e. the 3 ones, which is 3. Now that means it's 1 down and carry 1. We have to carry 1 to the next column. And now we add up this column here, and we can see we have a 0 plus a 0 plus the 1 that was carried, which gives us a 1. So we can see that the result of addition is shown here. Now when we add up, when we place what's in the column here, we refer to that as the sum. When we add up and we get a carry, then that obviously is referred to as a carry. Here we can see the schematic diagram of a half adder. Now it's referred to as a half adder because it is only capable of adding up 2 bits, i.e. it can perform this addition here where it adds a 0 to a 0. Likewise, these that I'm highlighting with the arrow, it can perform all of those additions. It cannot, however, perform this addition here. It cannot add up 3 ones, which is what we showed here in this particular addition, where we had a 1 plus a 1 plus its carry. Now the name half adder comes about because it cannot do this step. It cannot add up a 1 plus a 1 plus the carry. In fact, we need 2 half adders and a delay mechanism to allow this to work. But we'll not worry about that in this particular video. Here we're going to concentrate on the half adder, and we're going to be looking at what goes inside here. What is the combinational logic circuit that will perform the task of a half adder? Well, here we can see a truth table, and what we're going to do, we're going to relate this truth table to the schematic diagram that is shown here. Now the first thing we can see is that the schematic diagram has an input A and an input B. Likewise, we're going to have a look and see that the truth table has an input A and an input B. The outputs in the schematic diagram, well, we can see there's an output for the sum, so we have an output here for the sum, and we also have an output for the carry, which we can also show here in our truth table. So we can relate the truth table to the half adder schematic diagram. Now we need to consider all of the possible input combinations at A and B. Well, we've already really done that. They're these here, look. These are the possible input combinations, i.e. these are the combinations that we can add up. So we can come here and we can see that A can be a 0 when B is a 0, A can be a 0 when B is a 1, A can be a 1 when B is a 0, and finally they can both be a 1. And those are the possible input combinations for the half adder. Let's have a look at the first combination of A and B, and it's this one here when A was a 0 and B was a 0. Now we can see the result of this is a 0 as shown here when we did the addition right at the very beginning of this particular video. Now that will give us a sum of 0, and it gives us a carry of 0. Now when we're doing addition, we don't have to worry about the carry in the same way as we do when we're going to actually implement this using gates. If there's no carry, that has to be represented by a 0. If we now go on to the next combination, it's shown here, that's a 0 and a 1, and we know that that comes here, and we can see that gives us a sum of 1. So that's a sum of 1, and of course we have no carry. If we look at the next combination, well, that's a 1 plus a 0, which is more or less the same, except they're swapped around at the input. So that will still give me a sum of 1, and again, no carry. Now, if we have a look at the last one, which is here, which is the 1 plus the 1, well, that is this addition here. And here we can see it's 2, which is not possible to go in one column, if you remember. So what we said here, that we had a sum of 0 and a carry of 1. So on this occasion, we place here a sum of 0 and the carry of 1. Now what we've just completed is the truth table for a half adder. Using the truth table, we will now produce the sum of min terms for both the sum and the carry outputs. Let's deal with the sum first. Well, we can see we have a 1 on this occasion here. Consequently, we have the following min term. A ANDed with the B. But of course, if we have a look at the A, we can see that was a 0, and that should remind us that this should be not A. If we have a look again, we can see here that we have a 1 at the output here, the sum output, and that, well, that will be the input variables A ANDed with not B. Now why not B? Well, quite simply because we can see the B was a 0. And if you can't remember that, you need to refresh your understanding by looking at the previous videos in this particular playlist. Consequently, the sum of min terms for the output sum is as follows. We can say that the sum is made up of the two min terms, not a B, and I've missed out the AND symbol there. Remember, if the AND symbol is not there, it means they're ANDed together. But then I'm going to put OR, and then I'm going to put down the A and the not B. Now that is the sum of min terms for the sum output. Let's now turn our attention to the carry output, and we can see the only occasion when the carry has a 1 is here. Now that will give us the following min term. It will give us a min term of A and B. We can therefore say that the carry is indeed A, B there. A and B. I've missed out the dot in the middle, i.e. the AND symbol. Means the same thing. Now in this particular case, both of these expressions cannot be minimized. So what we can now do, we can build the combinational logic circuit that gives us these Boolean sum and min terms. And that will be what we stick in here, inside the half adder. So it's now simply a case of building the combinational logic circuit to implement these two expressions here. We take A and B and we put the A through a NOT gate to give us not A, and then we now produce an AND gate to give us at the output not A and B. We need another AND gate to give us A and not B, which involves taking a tap off the a tap off the B, but sending that through a NOT gate to give us not B. Then we take these outputs and we put them to the input of an OR gate, and that gives us not A and B, or A and not B. To implement the carry, we need an AND gate to give us A and B. Now this involves taking a tap off the A and also a tap off the B, giving the inputs A and B, which results in A and B at the output of the AND gate. Therefore, this is the sum output and this is the carry output. So we can say that we have related the sum and the carry as appropriate to their Boolean expressions. What we can see here is I've put this circuit inside this schematic diagram here, and now it's a question of connecting input A to here, input B to there, and actually arranging for the sum to come to the sum output here and the carry to go to the carry output there. So what we now can see is we've devised a combinational circuit that behaves like a half adder.